Combinations. So here we have something very similar to permutations. Combination is a selection of k objects from n options where order does not matter and repeats are not allowed. So notice the only difference from permutations is that now order does not matter. We just care about which k objects do we have, not what order did they come to us in. Right? As opposed to permutations, we cared about what order they came in. Right. So that's the difference between combinations and permutations. We have very similar notation, just how we wrote NPK for permutations. You could write NCK for combinations, which the way you speak this is, the way you say this is N choose K, right? So just a heads up, no one reads it as the C, they don't say NCK, you say N choose K, right? N choose K is something that you may have seen before. This formula comes up in sometimes in pre-calc or when you're doing binomial expansions, or calc 2, maybe when you do binomial power series, right? This n choose k notation with the large parentheses and over k. It looks like a fraction, but there's no bar written in between. They're just sort of stacked on top of each other. We have a formula for this. It's n factorial divided by n minus k factorial times k factorial. Or you could notice also it's over here. What is this? Another way to get it is you can do the formula for n permute k, right? Here is the numerator is the formula for n permute k. Take n permute k and divide it by k factorial. This is another way to do this. So these are both valid formulas, either the one with the 3 factorials or just the factorial on the bottom and n permute k up top. Why? Why does this happen? Well, this is one of these things I think best seen in an example. So let's look at an example and let's consider just all the ways of selecting 3 letters from 5, right? And we'll say that the 5 letters are A, B, C, D, E, right? Just to have names for them. So A, B, C, D, E are the 5 letters that we can pick from. And I want to look at all ways of selecting 3 of them. And I want to think about this both in with order and without, right? So with order, I'm thinking about permutations, right? When I say with order, I'm thinking about 5 permute 3, right? And without, I'm thinking about combinations, because I want to compare these two. As you notice up here in the formula, right? The combinations formula, it's coming from the permutations formula. So I want to think about this, all ways of selecting 3 letters from 5 where order matters and where order does not matter. And in both cases, no repeats, right? No repeats either. In either case, no repeats, right? So just, I want 3 different letters, right? And that's another way to say it. 3 distinct letters. Sometimes that's how people say no repeats, right? I want to select 3 distinct letters from 5 options, A, B, C, D, E, both where order matters and where order does not matter. So let's think about the permutation side. So let's think about 5p3. Oh, well, let's list them out. It turns out there aren't that many, right? So let's list them out. Let's start listing them out. There are quite a few, but not too many, right? Where I don't mind at least kind of seeing what the list looks like, right? Because this is, what would this be? 5 times 4 times 3. This would be 60 options, right? So I'm just using our permutations formula, the n permute k formula. So this would be the number of options. So I'm going to start listing these out. So what could I have? I could have A, B, C. I could have A, C, B. I could have B, A, C. I could have B, C, A. I could have C, A, B. I could have C, B, A. Right. And notice here, I'm not listing them totally at random. What did I do? I just listed in alphabetical order all of the permutations that use just the letters A, B, and C, just those first 3 letters, right? Well, all of those correspond to just a single choice over here, just A, B, C. If we're counting without order mattering, right? Because these are all just that one option, A, B, C, just that one selection, A, B, C, right? Here, on permutations, I cared what order they were chosen in. So I considered, say, these two as different, A, B, C, or A, C, B, I considered as different. But if I don't care about what order the objects are selected in anymore, now A, B, C and A, C, B are now the same selection, right? So A, C, B and A, B, C are the same selection. So let's just call it A, B, C. We'll just give it that name, right? And don't list out all these different ones anymore. We just have ABC corresponds to all. So the combination ABC corresponds to all of those permutations, right, that are shown on the left there. Okay, now let's keep going. So what do I have? What would I have next? Maybe now I'll do in alphabetical order all the combinations that use all the permutations that use A, B, and D. So I could have A, B, D, right? A, D, B. This is too many, clearly a bad idea. B, D, A, and D, A, B, and D, B, A, right? Well, again, all of these correspond to just a single combination, right? All of those permutations correspond to just A, B, D, just one combination, right? And I can keep doing this over and over and over again until I get all the way down to, right, and I'm thinking alphabetical order, right? So I'm going to get down to C, the permutations that use C, D, and E, right? So C, D, E, C, E, D, C, oops, D, there we go, D, C, E, D, E, C, right? E, C, D, and E, D, C. There we go. These all correspond to just the one combination C, D, E. Right. So now think about it. What do I have? It's always the same number of permutations, 6. It's always exactly 6 permutations collapsing into one combination. That's what's happening in every single one of these cases, right? And I already, now over here, I didn't know, before, well, I stated this theorem, but before stating this theorem, I didn't know the number of combinations. But look what happened. Over here, I already had a formula for this, right? I already had a formula for the permutations, right? It was 60, that formula told me. And now I'm collapsing them 6 at a time into combinations, right? So these will collapse. We're going to collapse 6 different permutations into one combination uniformly across our whole list. So what do I get over here? It has to be the number of permutations divided by 6, right? Or 60 divided by 6, which is 10. And that's going to be our number of combinations of 3 chosen from 5 is just 10, right? So this is our, this is the correspondence, right? This is why we're taking number of permutations, right? I'll count on n permute k and dividing it by something to get combinations. You're counting how many different orderings correspond to the same selection, right? Where it's just the same objects, but in a different order. You're dividing off by that factor. So that's what's happening here. Now, why in particular is it 6? Well, that 6 really is 3 factorial, right? It's just k factorial. How come? Well, because I have, if you think of this 6, say for the ABC, you could think of it as our little tree, how you think of A, B, and C. We have 3 options for the first letter. From A, you could then do B or C for the second letter. From B, you could do A or C for the second letter. For C, you could do A or B for that next letter. From A and B, you could do C. From A and C, you could do B. From B and A, you could do C. B and C, you could do A. C and A, you could do B. And C and B, you could do A. Right? And these strings, if you look at these words, like ABC, there's ABC. Right? If you look at ACB, there's ACB, and so on. Right? The tree diagram enumerates all of those 6 words. And if you look at the tree diagram, it's exactly 3 options times 2 options times 1 option, right? So that's why you have k factorial is what you divide by, right? So to get from, to say this another way, right? So note, what did we demonstrate here, right? To go from n permute k to n choose k, all you have to do is divide by k factorial, right? That accounts for reordering the k objects in any permutation, right? K factorial ways to rearrange those same k objects. So that's why those formulas are related that way. That's why the choose formula is just k factorial, is lower by a factor of k factorial from the permute formula, right? So that's our formula here for choose, right? Now, we can also check in this example. Let's check the above example by just listing. There are only 10 combinations, so let's just list them out and make sure that 10 actually happens. Right, let's check the above example by just listing. So I have that I have 3 letters chosen from 5, right? And especially where the 5 are A, B, C, D, E, just to be consistent with what we said above. What are all the options there? Well, I have, what would I have? I have A, B, C, A, B, D, right? A, B, E, right? A, C, D, A, C, E, A, D, E, B, C, D, B, C, E, B, D, E, right? And C, D, E. There we go. There we go. There we have everything, right? And if you look, this is exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there, we have the 10 options, and that 10 is exactly 5 choose 3 or 5 choose 3, however you want to write it. Right, so that's the 10 options here. And notice I wrote them out very systematically. If you ever do need to list something like this, the strategy always is just use alphabetical order, right? It's pretty hard to not miss one, I think, if you stray at all, or maybe there are other systems for enumerating them that can keep you organized, right? I find alphabetical order to be the best, right? Imagine these aren't all real words in the dictionary, right? But imagine they were, right? And then just list them out in an alphabetical order. So there's regular dictionary order. All right, so that checks our example above and shows how it relates to permutations. Okay, so I want to then comment on this, right? Like I said, you may have seen that before, right? You may have seen that before in the context of power series, or in the context of maybe Pascal's triangle, right? Binomial series, right? Binomial theorem, pre-calculus, calc 2. That notation comes up sometimes, right? So let's look at what is the connection there, right? What is the connection to the binomial? What is the connection to binomials? Well, here's what's going on there. Suppose you had 1 plus x to the 5th. So I'm still looking at exactly the same example. Consider 1 plus x to the 5th. What do you do when you take 1 plus x to the 5th? Well, you take 5 copies of 1 plus x and you multiply them together, right? And you FOIL everything out, right? And then combine like terms, right? So you do a giant expand, 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 and then you get some massive degree 5 polynomial, right? And what would be there at the end of the day on this huge degree 5 polynomial? You'd have a 1, right? You'd have a x to the 5th, You'd have a bunch of messy terms in between. What's the little trick for getting these, right? These messy terms in between. Well, it's Pascal's triangle, right? This is you may have seen this before, right? This is the very quick way to expand out a gigantic binomial like this is, right? Something that I don't really want to sit here multiplying all of those. So here's Pascal's triangle. I wrote it out to row 5. And what's great about Pascal's triangle is it gives you the coefficients on all the terms in between, right? So it'll be 1 plus 5x, you'll have 10x squared, 10x cubed, 5x to the 4th, and 1x to the 5th. And usually, write the 1 there, but I'm just writing it to show the correspondence with that row, right? So I was plucking the numbers out of that row in Pascal's triangle, putting them in as coefficients, right? And I claim now that 10 that we computed up here, right? I claim this is exactly that 10 there, which is not at all obvious at first. Here's the correspondence. So when you multiply these out, how could you get an x cubed? Let's think about how to get an x cubed. Well, an x cubed comes from choosing, right? There's the word choose, right? Choosing 3 x's to multiply together, right? X times x times x is x cubed. But choosing from where? Well, here I have 5 x's to choose from. And in fact, call them x sub a, x sub b, x sub c, x sub d, and x sub e, right? You don't, when we're doing algebra, you consider them all the same. So just x, right? But you could label them, right? You could give them a, imagine you're just still, it's x, but you're writing them in a different color pen or something, and we're just marking the color with a subscript, right? So they're not really different variables. We're just kind of keeping track of which x is which, right? Well, then how can you get x cubed? Well, you're going to expand this, meaning you're going to multiply this out in every way possible. You're going to mix and match a choice of multiplying a 1 or multiplying an x from each factor when you expand this, right? So if I multiply, say, for example, if I multiply x sub a times x sub b times x sub c times 1, that gives me a term that's x, that product gives me an x cubed, right? And that x cubed corresponds to a, b, c. Because I chose xa, xb, and xc, and I did not choose xd or xe to multiply together, right? How about if I did 1 times xb times 1 times xd times xe? What would that be? That would be an x cubed, and that x cubed would correspond to b, d, e, right? So what do we have? We have a perfect correspondence between x cubes that are generated by this product when you expand this product, right? And choices of 3 letters from 5, right? Every time you pick 3 letters out of A through E, you get an x cubed, right? By multiplying those x's, right? So x cubes, every x cubed comes from choosing 3 x's to multiply together, which corresponds perfectly to selections of 3 letters from 5, right? Now, also, we're supposed to have no repeats, right? What does that happen up here? Yeah, because, for example, you can't have BB, because I can't take XB, X sub B, and multiply it by itself. I'm multiplying XB by other XBs, right? So no repeats is good. Also, I want order irrelevant, right? This is good too. X sub A times X sub B is the same as X sub B times X sub A, right? It doesn't matter which order I multiply those in. It's the same quantity. It's just which x's have been selected, not which order did I select them in. So there we go. There's the link to right, to Pascal's triangle, to binomial series, right? So if you've seen this in the past where this expression gets written like 5 choose 0 plus 5 choose 1 x, right, plus 5 choose 2 x squared plus 5 choose 3 x cubed plus 5 choose 4 x to the fourth plus 5 choose 5 x to the fifth, right? If you've seen this in maybe pre-calculus, maybe in Calc 2, right? Yes, that 5 choose 3 is 10, right? And it's not coincidence that we're using the same notation. We're not just duplicating the notation in two different contexts. It's the same notation for a reason. They do mean the same thing. They do give you the same value. So, all right, there we go. So there's an introduction to combinations. This is just the tiniest tip of the iceberg. We will see way more, way more with combinations in lots of counting problems shortly down the road. So, all right, there we go. Combinations and linked to Pascal's triangle binomial series. Great, thanks.